Hello, this is second part of relative motion analysis for velocity. In the first part, we have seen how to calculate relative velocity using the equation VB is equal to VA plus VB with respect to A. So it's the same topic, but I'll explain this with the slides here. So we already talked about this example where everything is linear, and we talked about this one where velocity of B relative to A. Again, you can follow my cursor here. So velocity of B relative to A is pure rotation, but then A has linear velocity. So velocity of B with respect to fixed reference is combination of VA plus VB with respect to A. You can go through this quiz after the lecture. So the application. So this is a big engine, and the links of the engine are link BC, as you can see on the slide. Then this big rod, link AB, and the slider, which is link A. And question is, which link is undergoing general plane motion, link AB or BC? And the correct answer is link AB, because link AB has both translation and rotation. So then the next question is, how can the angular velocity omega, see this omega here, for link AB can be found? We'll talk about this same topic using the different example in this class. Another application of relative motion analysis is in planetary gear system. So this gear system is called planetary gear. The middle big gear is sun gear. That's why this letter S is written here. Two small gears which orbit the sun, they are called planets gears. You can see that letter P here. This arm connects two planets gear, and this is the shaft which is either driven or it's the input or output. And the outer big gear is called the ring gear R. This is very interesting mechanism because this gearbox is used in many automobile automatic transmission systems. By locking or releasing different gears, this system can operate the car at different speeds. You often have heard about 6-speed automatic or 9-speed automatic transmission in car. So those transmission boxes, they use multiple stages of the planetary gearboxes. With one gearbox, we can achieve 3 different speeds. So if a car has 9-speed gear, that means typically it has 3 different stages of sun and planetary gears, which are connected using the common shafts. There is an excellent videos on YouTube for the animation of how sun and planetary gears work. So you can go through that animation by following this link, or if you can't access this link, then you can just Google on, you can just type on YouTube animation of planetary gears, and then you will find nice colorful animation with the explanation of how does the system work. We have talked about this absolute position and relative position, and you are familiar with this equation. Velocity of B is velocity of A plus B with respect to A, and if link B has rotation relative to A, then B with respect to A is omega cross RB relative to A. Okay, so now let's look at this example. So this is very similar to the first engine example that we discussed in the class. So in this example, this link BC is called crank, link AB is connecting rod, and A itself is a slider. So A has pure translation and B has pure rotation, and AB is connecting A with BC. So link AB has general plane motion. So the question here is, how can we calculate the angular velocity omega for link AB? So there are two different ways. So this point B is very interesting point here because it's common point between link BC and link AB. So there are two different ways we can calculate the velocity of point B. So one way is we can just use the angular velocity of link BC and consider B as a point on link BC, and then using the pure rotation equation, that velocity of B is equal to omega cross R, where omega BC is the angular velocity of link BC, and RB with respect to C is position of B relative to C. In fact, C is a fixed point, it does not move. So we can also simplify this notation to just RB rather than RB relative to C, because as I have said before, that if the motion is relative to absolute motion, then we don't need to write slash absolute motion later for that. Okay, so if you just forget about link AB at this stage and slider and everything and just focus on BC, then this is the equation that can be used to calculate the velocity of B, provided that we know omega BC, because we always know the dimensions of the link. So we know the length of link, so we know position vector because we know the angle. Okay, so that's one option. Now the second way to calculate the velocity of B is through velocity of A. So at that time, don't consider link BC, but consider that point B is on link AB, and link A itself has a sliding motion. So A slides and B relative to A has rotational motion. So this, if you stand at A, you will see that B is rotating with respect to A. So the velocity of B can be calculated using this equation, that velocity of B, absolute velocity of B is velocity of A, this reciprocating velocity, plus velocity of B with respect to A, which is omega AB. So this omega here is actually for omega AB cross RB with respect to A. So if you look at the direction of this vector, then it's the arrow which goes from A to B. So B relative to A. So there are two different equations. Now since point B is a common point between both the links, this velocity must be same. That means we can equate omega BC cross RBC with VA plus omega cross RB with respect to A. Now when the engine is designed, we already know the lengths of link BC and link AB. So we have the information about the position vectors. It's very easy to measure the angular velocity of link BC because it has pure rotation. So we know this information as well. And now it's also easy to calculate or measure the sliding speed of A. So we have this information known as well. So the only unknown, if when we equate this equation with the bottom equation, is the angular velocity of link AB, and by equating these two we can determine angular velocity of link AB. Don't worry about this part if it's not clear yet, but just try to understand the theory portion itself. Don't worry about the equation so much, because we will do in-class exercise and we'll actually apply this equation and calculate the velocity. So this slide has the same explanation which I have just given. Consider another example where this wheel it rolls on ground without slipping. So look at this point A. Again, follow my cursor. So look at this point A. This green is ground. So point A is contact with the ground. We have studied previously that when two rotating parts, like two objects, are in contact, at this common point of contact, it must have the same velocity. That means velocity of point A must be same for both wheel and the ground. And ground does not move, so the velocity of ground is 0, and so is the velocity of this point. So even though the wheel rotates, at the given instant, at this second of time only, A does not move as long as A is in contact with the ground. So velocity of A is 0. Since there is no slipping, point A has 0 velocity. So that's what we have discussed. Now, how can we calculate the velocity for the center B of the wheel? So furthermore, point B at the center of the wheel moves along a horizontal path. Okay, you can see that B does not go up and down because it's at the center, so it just moves along the horizontal path. So thus, VB has known direction, example, parallel to the surface. So how can you calculate the magnitude of velocity B? So we can apply this equation, that velocity of B is nothing but velocity of A plus velocity of B relative to A, because B has this link, AB has rotation. So velocity B rotates relative to A. So we need to apply this equation omega cross RB relative to A, where RB relative to A is nothing but the radius of the wheel. And for this specific example, because VA is 0, this part is 0, velocity of B is nothing but omega cross R. That is angular velocity of the wheel multiplied by cross product with the radius of the wheel. So now I ask you one question. So imagine that there are two bicycles or two bikes. One bike has bigger wheels, the other bike has smaller wheels. So radius of wheel for one bike is higher and radius of wheel for another bike is small. If we assume that both the wheels of both the bikes have the same angular velocity, omega, then which bike goes faster? Which bike has higher velocity? I repeat the question. Two bikes of different sizes of wheels, big wheels and small wheels, if both the wheels rotates on both the bikes at same omega, same radians per second, which bike runs fast on the road, or which bike has higher surface speed or velocity? You can pause the video and think about it before I give you the answer. Okay, so this is the situation. So one bike has bigger wheels, another one has smaller wheels. Both the bikes, they have same omega. So velocity in the previous example, we have seen that velocity of B, that is center of the wheel, is omega cross RB slash A, that is angular velocity of the wheel with the cross product of the radius of the wheel. And because the center of the wheel is attached with the frame, and the biker also rides on the same frame, so velocity of the entire bike is same as the velocity of the center of the wheel. Okay? And in both the cases, we have the same omega, so one which has higher value of R will have higher velocity V. So bike with bigger wheelbase has high speed compared to with smaller wheelbase, provided that both the wheels rotate at same angular velocity omega. So now for the next two slides, we'll talk about the procedure for the analysis of relative velocity equation. You can read the description. I'll make it simple. So the first step is you define your coordinate system and draw the kinematic diagram. Second step is, this is the scalar approach. So we don't use I, J, K coordinates here, but we break down velocity components into X and Y separately. And the second part, the first step is kinematic diagram. The second step is you write the equation for velocity of B separately for X and Y coordinates, and then you solve for unknowns in step 3. So this is the scalar analysis. So there is no cross product in here, just pure scalar solution. For vector analysis, we do the same thing. We define the coordinate system, we draw kinematic diagram, and then next step is write the vector equation that velocity of B is velocity of A plus omega cross RB relative to A. And then evaluate the cross product with and equate respective I and J components to obtain two scalar equations, and then finally solve for the unknowns. And if the answer is negative, then the sense of direction that we originally assume is opposite to the real sense of direction. So you basically change the direction. And if the answer is positive, our original assumption is right. Okay, so with this information, now we will do in class exercise 1